In this video, we're going to look at two questions on the topic of electric fields. So, firstly, it says three conducting spheres or radii, a third r, a half r, and r are mounted on insulating rods and are well separated from each other. The third r and r spheres are each charged to a potential V, whilst the half r sphere is uncharged. Then a thin copper wire is used to briefly connect all three spheres. What fraction of the original charge on the two spheres is now on the half r sphere? That is what the question wants to calculate. So let's say there's three spheres. I'm going to draw a sample diagram. So this is the largest one, that is r, a half r, and then a third r. Okay, let's say it's just like this. So basically this will be V, V. And let's label these. So this is sphere 1, 2, and 3. Now the idea is that once they're connected to each other, charge will flow from the first and third sphere to the second sphere. And then the principle is that this system will reach equilibrium when the three spheres all have the same potential. And in this case, the question wants to calculate the fraction of the original charge on the two spheres. So I suppose that is the total charge initially that is transferred to the second sphere. So to start, we can get some clues from the equation for electric potential. And in this case, this is just kq over r. So my idea is that we can establish an equilibrium between the charges, the initial total charge, and the final total charge. Yeah. So, and then we can express it in terms of this. So if we isolate Q, that will be equal to VR over K. So initially, let's look at sphere 1. So for sphere 1, let's say it is just Q1. It is equal to V, and then its radius is just R over K. And then for Q3, that is simply just V a third of R, so therefore that's 3K. Now, yeah, that's the idea. Now, how do we actually establish an equilibrium? So the final state of a system, each sphere, let's say, it will have a potential of V dash. Okay, so how do you establish an equation? Let's say the initial total charge is just VR over K plus VR over 3K from over here. And this is equal to, okay, so that will be V dash times R. So this is for the first sphere. And then for the second sphere, it is V dash R over 2K. And then for the third sphere, that is V dash R over 3K. Now, we can cancel out all the R over K's. So on the left side, what's left will be 4 over 3 V. And on the right side, that will be 1 plus a half plus a third. That will be, so that is 5 over 6, and plus 1, that will be 11 over 6. And then it's V dash. So therefore, we can express V dash in terms of V. And that will be times 6. Okay, I'm just going to do this. That will be, and then times by 6 over 11. And this will be equal to 8 over 11 V. and we calculate v dash, so that is the final potential of each of the spheres. Now we will be able to calculate the charge on the second sphere. So the charge on the second sphere will be 8/11 v. This is the charge. No, this is the potential, and the potential is equal to kq/r. So kq, q, let's say it's q2 over, it's a half of r, so therefore it's like this, and then so therefore q2 will be equal to that'll be 4/11 times, this is VR over k. Now let's look back over here. So we want to calculate the fraction of the original charge. The original total charge is VR over k plus VR over 3k. So it's over here. So basically, this will be equal to q1, let's say q total will be equal to 4/3, and then it's VR over k. Therefore, the fraction would be, we can cancel out the VR over k, so therefore it's 4/11 over, that is 4/3, and that will be equal to 3/11. And this will be the answer to the first question. Now let's look at the second question. Over here it says, two well-separated identical conducting spheres radius 10 centimeters are charged to plus 200 V and plus 400 volts. So these are the electric potential, and then these are electric potential of two identical spheres. And then the question wants to calculate, if they are joined by a long wire, how much heat is generated. So heat is essentially energy, right? So let's see. Let's say the energy in this case, for these kind of setups, essentially some kind of circuit. So this will be equal to V times Q. See, in this case, we will be able to calculate V, maybe, and then for Q, no, it's not actually possible. Yeah, I don't think we can actually calculate Q. So let's change to another idea. So essentially, this case or context is similar to the previous question. So the idea is that some of the charges from one of the sphere will flow to the other one, and I suppose we can compare this kind of situation to like capacitors. So what we can consider is that there's two capacitors. Let's assume there's two capacitors and somehow connected with a wire, and then the idea is that this stores a potential of 400 V, and this is 200 volts. And so therefore, charges will go from the left to the right. Now let's see. So we will be able to calculate heat if we actually can calculate the capacitance. And I think this is actually possible. So capacitance, what we know is that there's an equation of which it is equal to epsilon times area over d. And we can actually apply this to a sphere. Yeah, so basically, in this case, the capacitance will be equal to epsilon, and the area will be equal to 4 pi r squared. So 4 pi, let's see, 0.1 squared over the distance. Distance will be the radius. Yeah. Okay. So this is the capacitance, and we can convert it to a numerical value. So over here, epsilon will be equal to 8.85 10 to the power of negative 12, and then timed by 4 pi. Pi is over here, and times by 0.1 squared. Then down there we have another 0.1, and that is equal to, I'm going to leave it for 3 decimal places, so that's 112 times 10 to the negative 11 farads. So, okay, now what we know for capacitance is that the energy stored by a capacitor is equal to a half CV squared. This is the energy stored by a capacitor. So the heat in this case, the heat generated is basically the amount of energy that is lost throughout the process. And okay. Now, another thing we have to understand is that we have to calculate the initial energy and then subtract it from the final one in this case. So let's see, E initial will be equal to a half, and then C, which is V squared. So in this case, that will be equal to 200 squared plus 400 squared. And this is equal to 0.1, so 0.5 times 1.112 negative 11 times 200 squared plus 400 squared. And that is 1.112 times 10 to the power of negative 6. And E final, in this case, I suppose when their potential are equal to each other. So that will be, yeah, so that will be 300V from common sense. That's 300V, so that will be a half C. I'm going to write C for now. And then that is 300 squared times 2. And this will be equal to, so here, that will be 300 squared times 2. And that is 1.8 times 10 to the power of 9 minus 6. And the difference in V will be equal to the heat generated, heat lost to surrounding, and that will be equal to 1.112 minus 6 minus ants, and that is 1.112 times 10 to the power of negative 7. And this will be the answer to the question.